Hello and welcome to my talk. My name is Thomas Grange from nextnano.NEGF, and the title of this presentation is Microscopic Modeling of Interface Roughness Scattering and Application to the Simulation of Quantum Cascade Lasers. So first I want to give the outline. I will first remind the importance of scattering processes in quantum cascade lasers. I will then show how interfaces deviate from the ideal case in real devices. I will then present the general theory of interface roughness we have developed in the presence of grading. And I will then introduce the simulation of quantum transport using the formalism of non-equilibrium grid functions, NEGF. And finally, I will show the influence of interface roughness in the simulation of QCLs. So first, I want to introduce the working principle of QCL. So these devices are based on the following picture. If we look at the structure along the growth axis, so we have a repetition of a periodic system where a lasing transition can be engineered between two states, and we can have some optical photon emission, and the carriers are recycled from some pass through some minibands through the next period. And if we look along the growth direction in this picture, we can understand how the current transport works in terms of tunneling and how the radiative processes work in terms of photon emission and absorption. But if we want to understand also the non-radiative processes, we need to look at what happens in the plane. So indeed, as we have a 3D device, we need to consider also the in-plane dispersion. So if we look at two particular states here, they are in fact attached to a sub-band dispersion, so that is the dispersion in the plane where they are free to move. And importantly, given carrier can scatter from one state to another by either elastic scattering, that is conserving energy, or by inelastic scattering by means of, in particular, phonons. And here in this talk, we will be focusing on the effect of interface roughness that can induce such elastic scattering. And if we account for this picture, then we'll be able to model the full dynamics of the carrier transport in such device. Now I introduce the different scattering processes that are present in quantum cascade lasers. So you have optical phonons, alloy disorder, interface roughness, charge impurities, and electron-electron scattering. And out of these different possible mechanisms, most of them can be described through the intrinsic material properties, and in particular optical phonons, for which the scattering term is well established in terms of the intrinsic material parameters. Whereas for interface roughness, it's more complicated because the actual scattering parameters will depend on the device. And the interface quality is crucial for all heterostructure application because as I said, this non-ideality of the surface interface will induce scattering. And in quantum cascade lasers, the interface roughness is known to limit the lifetimes and hence the performances through the current threshold and the output power of the laser. So how an actual interface can deviate from ideal one? So you have two effects possible. So first, you have the roughness, and second, the grading of the interface, so the diffuse nature of interface. In the case of interface roughness, here, so the position of the abrupt interface will depend on the in-plane position. And this will break the in-plane invariance of the device, and as a consequence, it will induce elastic scattering. On the other hand, a diffuse interface or a graded interface means that the interface is not abrupt anymore, but in this case we can still model the interface as in-plane invariant. And in this case, we don't have scattering, and we just have different energies, because when we go from the square potential to the graded case, then the energy levels are shifted. In this work, we want to combine these two different effects to combine them into a general theory which account for both this rough and diffuse nature of interfaces. So first I will come back on the standard case of interface roughness, where so we have this abrupt interface, which can be modeled through a height deviation that here we call h. And if we treat this perturbating potential into the Famigonian rule, then we can express the scattering rates between two states in terms of this square potential, which involves delta square, where delta is a root mean square deviation of the height with respect to the average position of the interface, and lambda square, where lambda parallel is the in-plane correlation length. And here is the sum over all the interfaces, because there is no correlation assumed between the different interfaces. And so because this is a standard approach which is found, for example, in this reference. So now I will introduce a more general model about interface. But first I want to introduce the model that was developed by Valavanis and co-workers in this paper, where they assume that the log profile was the same everywhere. It was just that it was shifted. It was rigidly shift for each position. So in this case, assuming such profile, we're able to derive a model still based on the two parameters, that is root mean square deviation delta and in-plane correlation length lambda. However, in reality, it turns out that the physics is more complex, because for different position, the log profile is not only shifted, but it can have different shapes. And we show that, in fact, you need a third quantity to describe to characterize the roughness, and this is a Gaussian function along the growth axis that we will introduce later in this talk. First, I want to give another picture of these two cases. So I go back on this model of Valavanis. So in this case, if you define a different isoconcentration surface through the interface, this model is equivalent of assuming that these different surfaces are of the same shape. In the more general case, in the model that we have developed, we are able to model the case where these different isoconcentration surfaces are not necessarily fully correlated, and because in fact we will introduce this correlation lengths that can be smaller than the interfacial width. So we, as I said, we still consider this deviation height from the average isoconcentration surface h, except that now this h can be defined from any isoconcentration surface and not only from the interface. And what we want is to express the perturbation that breaks the in-plane translational invariance. So this delta V is given by a difference between the actual potential profile minus the average, the in-plane average potential, which is translational invariant and which doesn't break which doesn't induce scattering. So if we linearize this term at first order, we can express it as a function of the derivative of V, of the potential, times h, the height deviation. And now if we plug this into the matrix element between two states alpha and beta, we are able to get such expression. And from this, to calculate scattering, to calculate some square matrix element, delta V squared, which is given by the following expression. And in this expression, we have a product between two height deviation. And so this is a 3D correlation function. And in this work, we assume that such correlation function, that such 3D correlation function, can be separated into two parts, an axial correlation part and an in-plane correlation part. This assumption is based on the fact that these two length scales are very different. There are almost 2 orders of magnitudes larger for the in-plane than for the axial part. And in fact, this 3D correlation function can be measured experimentally. For the axial, so here we have atomic probe tomography, which has been carried, and the axial correlation function has been measured through the measure of the different isoconcentration surfaces, and we have been able to extract how such points for the isoconcentration for the axial correlation function, and to fit it with mono-exponential decay. And we have extracted this correlation length, about 3 angstrom. Whereas for the in-plane correlation function, this behaves in a similar way as for abrupt interfaces, where we have a Gaussian correlation function with a long scale of a few nanometers. And here the important information is that the axial correlation function can be actually smaller than the interface width, and this further motivates the use of a general model for interface roughness in the presence of such graded interface. So using these correlation functions, we are able to get an expression from the scattering rate between two states, which is obtained through the Fermi-Gordon rule. And in this expression, we have two influence of the correlation lengths. So first, here we have the influence of the in-plane correlation length, and this dependence is the same as we had already for the standard case of interface roughness. So we have this dependence where we have an increase here because of this lambda squared term, and then we have a cutoff here, which happens when the in-plane correlation length matches the inverse exchange momentum, and then a decrease. And here we have a new term due to the axial correlation length. And in fact, this term gives such dependence where at very small axial correlation length, it goes to 0, because it means that the different contributions of the different isoconcentration surface tends to cancel. It increases then, and it turns out that there is a maximum which corresponds to the typical thickness of the layers which is involved in the device, and then it decreases because the contribution of two consecutive interfaces tends to cancel out. So before seeing how we can plug in this new description of interface roughness into simulation of actual device, I will come back on the different methods that can be used for simulating QCLs. So first, the simplest model is given by rate equations for populations. So this is a semi-classical picture for transport, because no covariant transport is accounted. Then we have this density matrix formalism, where covariant transport can be accounted, but it's difficult to account for scattering and dephasing processes. And the most advanced formalism is given by non-equilibrium Grace functions, where coherent description of transport is provided. All scattering processes can be calculated on a microscopic level, so that is without phenomenological parameters, accounting for energy conservation. Self-consistent description of burning effects are also accounted, and electron heating is also self-consistently accounted. So how this works in practice? So if we start from the Hamiltonian of the device, it can be separated into a part H naught, which is the one carrier Hamiltonian that can be exactly solved through the K.P model. And we have also a mean field electrostatic potential, which can be also exactly solved. And we have a third part, which is due to scattering processes, which cannot be exactly solved, but which can be treated through self-energies. So this includes the different non-additive scattering processes due to phonons and disorder effects, and in particular interface roughness. And the NEGF formalism is based on self-consistent equations. So we have two important equations, which are the Keldysh equations and the Dyson equations. So the Dyson equation allows to calculate the retarded self-energy, the retarded Green function based on the retarded self-energy and the electrostatic mean field potential. And the Keldysh equations allows to calculate G lesser, that is the charge density, based on the knowledge of the retarded Green functions and the lesser self-energies. And these different quantities are linked self-consistently because the charge density induce a different electrostatic potential, which in turn is plugged into the Dyson equation, while the self-energies are linked to the calculation of the lesser Green functions. So once these self-consistent equations are solved, we are able to extract physical observables such as current density and gain calculation. But now, if we want to introduce lasing above threshold, we need to account for the electron cavity interaction, and this is done here through the gain clamping condition. That is, the calculated gain matches the optical losses of the cavity, and using this condition, we calculate the cavity electric field, which in turn induce relative scattering. So we have a new self-consistent loop, and at the end, when convergence is achieved, we have in addition the emitted optical power and the wall plug efficiency. So now we have applied this NEGF formalism. We have incorporated the general model of interference roughness, and here we look at mid-infrared QCL design of this paper. And on the left, we have the abrupt interface case, where we have all abrupt interfaces, but considering interface roughness. And on the right, we have applied the general theory of rough and diffuse interfaces. And interestingly, you can see that both scalar density and also the emitted power. So here we see the emitted power as a function of the potential drop applied through one period. And we can see that these physical quantities are affected by the shape of the interfaces. And here it's important to point out that we have very thin layers, which are comparable to the interfacial widths. So it's not possible to to distinguish between the different interfaces anymore, where we consider interface widths of 0.5 nanometer. So in this case, it's important to have such a general model of interface roughness to be able to describe the actual influence of these scattering processes. Now we can look also at the influence of the axial correlation lengths on the QCL performances. So here we have plot the wall plug efficiency of the laser as a function of the axial correlation lengths, and we see here that for very small correlation lengths, the interface roughness has little effect because the different contributions tend to cancel out, whereas increasing the axial correlation length, we have a decrease of the wall plug efficiency because we have more dephasing and shorter lifetimes. And here in particular, we see that we have a much larger browning due to interface roughness when the axial correlation length is of the order of a typical barrier, the thickness of a typical barrier in the device. And then the effects decrease again, and then the wall plug efficiency increases again when this axial correlation length increases, because then then it means that two consecutive interfaces tends to be correlated again, and so the effect decreases. So the message here is that interface roughness is important, very important in quantum cascade lasers, and that this generalized model enables to accurately describe the effect of such roughness. So to summarize, I've introduced a generalized theory of scattering by rough and diffuse interfaces. I've shown that such microscopic modeling of scattering can be included into an NEGF simulator. And finally, I've shown that the interface properties have important consequences on the performance of quantum cascade lasers. And for more details on the interface roughness model, I invite you to look at the following paper. And for more details on the nextnano NEGF simulator, you can look on the nextnano website. And finally, I thank you for your attention.